So next up, we've got Sebastian Winter from DNV.
Hi everyone, I'm Sebastian. I'm an AI researcher at DNV, and this afternoon I'm going to present a little bit about how we can make better designs by measuring and reducing uncertainty. So I have to admit I'm a little bit nervous because I'm standing between all of you and lunch, but I'm hoping by the end of this session you'll be convinced it was a good use of your time. So first I'm going to explain a little bit about who DNV is and why we might be interested in uncertainty. And then I'm going to talk about some work we've done over the past few years about trying to use uncertainty to make better decisions in an engineering context. So who is DNV? DNV provides technical expertise in engineering and assurance to make sure things are safe and reliable, and these are some of the industries that we have a big presence in. So, for example, I think 30% of new build ships are built to our standards. We're involved in almost 90% of offshore wind turbine projects worldwide. And we don't own or operate any of these things. Our job is to come in and tell our clients and our operators if this thing is safe and fit for purpose. And that's what I want you to think of when I say the word assurance: safe and fit for purpose. So we have a research team within DNV, and that's where I sit. And what we're interested in is, how does AI change our ability to assure things? So we have about 60 researchers who work on this full time, and we have a variety of backgrounds from computer science, AI, risk, assurance science, etc. And broadly, we're interested in two questions. The first one is, how can we perform assurance with AI? So an example of this might be using drones to inspect a ship to make sure that there's no cracks or defects. One of the other areas that's starting to emerge is, how can we assure AI itself? And this becomes increasingly important as our clients embed AI into their assets. So an example here is, as we start to see autonomous control within ships, what do we need to do to make sure that this system is still safe? And what do we need to know about the AI in order to start assuring this? So some of the things that make this difficult is that AI has kind of sprung up out of this virtual environment. That's what I'm going to call it. What I mean by this is domains such as web or gaming, and what this is characterized is that the cost of mistakes is often quite low, and the cost of deploying fixes is quite cheap, and it's fast to do. In these scenarios, we also often have a large amount of data, which is cheaply available. So what this has led to in this domain is this kind of iterative or agile or move fast and break things type mentality. And this has shown really good results in this domain, and a lot of the developments we see in AI have come from this type of way of working. What that's led to is we often use AI that just works. We don't necessarily know exactly how it works, but maybe we have enough data that we're reasonably confident in its average prediction, and perhaps the cost of it making mistakes is something that we're comfortable with. In comparison, our clients exist in this physical domain or this physical world. And what I mean by that is it's governed by the laws of physics or the laws of nature. And in this environment, we have a cost of making mistakes that's often severe or life-threatening. In addition to that, the ability to deploy fixes is often slow and expensive. So, for example, if you design a wind turbine using AI and then you realize some of your design is wrong, it's going to be a huge headache to then go and fix that when they're offshore. In addition, data can often be scarce or expensive to get. So what this leads to is we have a greater need for assurance because we have greater risks. But the tools we use in the virtual domain of being able to do trial and error or having a lot of data are no longer so available to us. So what can we do to deal with this? So this is why we care about uncertainty at DNV, because we see it as a path to navigate some of these challenges. And it's two things that we get from doing this that's quite useful. The first is, in this physical domain, often we just have to live alongside a lack of knowledge. Maybe we have a small amount of data, or there's physics we know we don't fully understand. And this gives us a way to represent that. And then what we can say is, well, given the knowledge or the data I have on hand, this is the most I can tell you at this point. The other thing that it lets us do is it lets us reason about this cost of making mistakes. What we can then do is imagine the plausible scenarios we might be in and understand what are the costs of our decisions in this scenario. So for example, imagine you're designing a structure and you have a distribution over the true strength required. What you can then do is say for a candidate design, what is the chance that the required structure is more than my design, and the cost of that is going to be very large. Your structure might fail. On the other side, if your candidate design is stronger than it truly needs to be, you also incur a cost because you're using excess steel or excess concrete. So it allows us to start weighing up these considerations and minimizing it. So now that you know a little bit more about D&B and why we care about uncertainty, I'm going to go through some of the work we've done over the previous years looking into this. And this is quite a nice problem because it's sprung out of one of our business units. We then did some research. We've released an open source package related to this, and we're now going back to that business unit to see how it performs in the real world. So I'm going to start with an illustrative example, and towards the end we'll talk more about how this might generalize. But what I want you to think about is you're designing a wind turbine to operate somewhere in the North Sea for a period of 20 years. And what you need to understand is how strong does this structure need to be to survive that duration. So what we're interested in is what is the most extreme or largest response this structure has to its environment over this lifetime. Now this value is a distribution, like we can see here on the right, and that's because the exact weather that you're going to experience over a 20-year period is unknown. So this is called the extreme response distribution, and typically we're interested in some specific quantity. We call this the quantity of interest or the QOI, and that could be the mean or a quantile. It's not really that important. So if we're interested in getting this value, what is one way we could go about it? Well, in an engineering scenario, typically we have information about our weather or environment distribution, and we often have very accurate engineering simulators. So these could be finite element models. So these are very accurate, but they're often quite slow. So what we could do in this situation is we could take 1 hour of average weather data, feed it into our simulator, and get the response in that 1 hour. We can then repeat that process for 20 years worth of data and take the maximum response we got. We then have one sample of this extreme response distribution, and we can collect more samples by repeating this process. The challenge with this is that it requires approximately 10 million runs of our simulator. And if our simulator takes 1 minute of runtime to simulate 1 hour of real-world operation, then it's going to take approximately 20 years to run this simulation. Obviously, you can do smart things like parallelize this and etc., but the computational and time cost starts to get just too big. So that means we need to approximate this process in some form so that it becomes feasible. One way we can approximate this is by making a cheap copy of our true simulator, and this is called the surrogate. So one way of making a surrogate is using machine learning, and so what we then do is we run our simulator at a variety of points. We collect the results, and that gives us a data set to then train some machine learning. That machine learning then slots into that process that I just described and replaces the simulator. So now we can run this naive process, but with a surrogate model that means this is fast enough to give us results in a feasible amount of time. One of the challenges this introduces, though, is that we now have uncertainty about how good our machine learning model is. You can see on the example on the left here, we don't have much data and it doesn't really truly match the simulator that well. So if we don't fully trust our surrogate model, then how can we trust the values that we get from it? That's the challenge we now introduce. So to the rescue, uncertainty-aware machine learning. So in the top example here, we have a representation of our surrogate model, and then we show on the right what is the extreme response distribution we get from it, and how does this compare to our true extreme response distribution? And what you can see is that the blue distribution is quite narrow, so it's confident, but it's also very wrong. It's a long way from this grey distribution. And this is really problematic for us in our environment. We don't want to be confident and wrong. So instead, if we introduce a uncertainty-aware model, like we see here, then we can start to propagate the uncertainty that this model has through to the calculations we're doing. And what we then have is an extreme response distribution that's much wider, but now it actually reflects the confidence we have given the amount of data we have on hand. So this is much more useful for us. And in order to do this, we use Gaussian processes because they work well with small amounts of data, and we can also incorporate some prior belief which we might have in an engineering context. So the next problem we encounter is that Gaussian processes work best when the error that we're talking about is Gaussian. And we often encounter situations in this context where we have non-Gaussian noise. And it's really important for us to appropriately handle this noise, because when we're working with the extremes of a problem, we're often in the tails of our distribution. So what you see here on the top example, in the top row is our true model. And if we put the same input in and run our simulator multiple times, we start to understand what kind of distribution do we get for our output. The way we can use a Gaussian process to get this non-Gaussian distribution is we use it instead to fit parameters of a distribution. So now we have a surrogate model that uses GPs internally, but can give us a non-Gaussian likelihood or error that we can then work with. Cool. So we've talked a bit about surrogate models, how are they, what are they, and how might they work in this situation. But what do we actually get from going to all this effort? People have been building wind turbines for a long time, so there has to be other ways of going about this. So here I present a little bit of work that we've done on a case study comparing this approach of surrogate models to an industry approach. What we found is Bayesian optimization gives us a more robust solution than environment contours, which is a common approach for designing these things offshore. And what I'll do now is I'll explain a little bit of the intuition as to why this is. So on the left here, we see this x-axis contains the weather. And one way that we can generate an extreme response is if we have extreme weather, and then we have a typical response from our simulator. This represents the box plot of our simulator's output. We can also generate an extreme response if we have common weather conditions and atypical simulator response. And the good news with the surrogate model is that we can handle both of these situations and any of the variants in between them. In comparison, environment contours only considers this situation where you have extreme weather. And that's because instead of approximating the simulator, it approximates the environment distribution to just look at the most extreme conditions and see what happens in them. So what we see here on the right is where in our environment space does the environment contour think that the most extreme results are going to occur. What we can see on the heat map is where they actually occur. And what you can see is that the true occurrences are within this boundary. So this shows that this assumption here is broken and there's some influence from the simulator. This is known to engineers, so this is not a new problem, but one of the challenges is it's problem specific how much these assumptions are going to be broken. It depends on the specific problem you're working with, and this is really hard to know beforehand. And so engineers then have to allow some margins of error or some safety factor, but it's basically down to their experience how big that should be, and that's a challenge. So we've talked a little bit about surrogate models and how we can use them to measure our uncertainty and what are some of the benefits of doing that. But the big challenge is that it introduced new uncertainty into our process. So now we're going to talk about how can we go about reducing that uncertainty in a smart way. So our surrogate model is built on data. So as we collect more data, it gets more certain, and the calculations we perform with it then also become more certain. Somewhat counterintuitively though, is that points that have the most uncertainty in our surrogate model, if we collect them and reduce a lot of uncertainty in our surrogate model, doesn't necessarily translate to reducing the most uncertainty in our quantity of interest. So what we can see here on the left is our surrogate model and 2 points we're considering collecting. And on the right, we see what would be the result of collecting those points and then running our calculations. And then we see, even though this green point would reduce a lot of uncertainty, the extreme response distribution it results in is wider than the purple one. So this is an important point because we're not just interested in the uncertainty in our surrogate model, but how that interacts with the uncertainty in our quantity of interest calculation. We care about the points in our surrogate model where their uncertainty has a really big influence on our quantity of interest. So we could collect data randomly, or we could collect it with some expert opinion, but what we really want is a system that tells us which data point it thinks is going to be most likely. And as I'm sure you're all aware, this is active learning or design of experiments. So how can we collect this data? We want an acquisition function or a heuristic that tells us which points are likely to be useful. Now, we could come up with some kind of smart heuristic that can kind of directly tell us this, but it's really hard to get one of these that works across a wide variety of domains, especially when we consider different quantity of interest calculations that we might be doing after we make the model. So we can perhaps sidestep this approach of coming up with an all-knowing quantity of interest, an all-knowing acquisition function, by instead coming up with a very simple heuristic of how beneficial a data point will be, and then running that for a large number of data points. So taking a kind of brute force approach. So in order to do that, what we would need is to be able to guess what kind of data point might we get back from our simulation, and then we need to be able to quickly calculate what impact might that data point have. What is the uncertainty I get after that? So the good news is the first part of understanding what kind of data points will we get back from our simulator, the GP does exactly that, right? So that part of the problem is already handled. We're then left with the question of, okay, how do we quickly calculate our quantity of interest? And we talked about the naive approach previously, and that's one way that we can calculate our quantity of interest. But now that we're doing this within an optimization loop, we'd ideally like something faster so that we can run it much more and do a more exhaustive search. So what can we do about trying to get something a bit faster? So what we found is that with the help of a bit of maths, we can get a faster quantity of interest function, and that helps us explore the space better. And this is a snippet from a preprint we have out. And you can see the core equation that lets us do that over here. I'm not going to get too stuck into that equation. Instead, what I'm going to do is provide a bit of an intuition about what this is doing and how it works. So imagine that we had a CDF that, if you have a simulator that runs for 1 hour, it can tell us what is the probability of your structure surviving that 1 hour period, right? So if we can get this CDF, then we can really easily start to extend to different lengths of time. If we want to understand what's the likelihood of surviving 2 hours, well, that's just surviving the first hour and then surviving the second. And so we can then take our CDF to the power of how many time steps it has to survive. So this lets us really quickly go to long time periods, which is important if our simulator runs for an hour, but we're interested in the 20-year result. Cool. So these first two works that I've covered have been academic contributions, and we've written some papers about this. But what we'd really like is to be able to get this into the hands of people so that it can be used in the real world. And that's what this next section is going to talk about. So we've developed an open source Python package called AxStream, and this stands for Ax for Extremes. And what this does is it extends Ax, which is a popular Bayesian optimization tool from Meta, to incorporate some of these academic improvements into a tool or a framework that's friendly for engineers to use and start applying to problems. So building on Ax gives us a really good foundation that handles a lot of the bookkeeping, its well-known interfaces, and what we do on top of that is put in some of our developments about how do we handle non-Gaussian noise, how do we calculate quantities of interest from those GPs, and how can we use the design of experiments procedure that we just talked about. So what might you get as a result from using this package? So this is the results that you might get from that illustrative wind turbine example. And what it shows is how the uncertainty in your quantity of interest estimate decreases as you perform more and more simulations. So in blue, we have our baseline, and that comes from using a Sobel design to select new points. And then in green, we have our design of experiments approach. And the key thing I want to draw your attention to is that both of these methods have been stopped once they hit the same level of uncertainty. And the important thing is how many simulations did it take to get there? And you can see that the design of experiments gets to that level of uncertainty much more quickly. So what might engineers do with this information? Perhaps they might choose to continue running simulations because they want to get to a very, very small level of uncertainty and a high level of confidence. Alternatively, they might have a threshold that they need to be below or under, above or below. And once the confidence region excludes that threshold, maybe then they're happy to stop. So there's a variety of ways that this can be used, but in general, being able to reduce this uncertainty quickly is a helpful tool for them. So I've talked a lot about wind turbines, and some of you might be scratching your head and saying, all right, I don't work with wind turbines. Is any of this applicable to me? And my answer to that is, I think it will be. So this is particularly well suited for problems where you have expensive black box simulators. And what you need to do is understand their behavior over a long time frame, potentially under the impact of random inputs. So in our case, weather conditions. There's some different examples that come from our domain of where this is useful. So hogging and sagging of ships, which is how do you make a ship strong enough that it doesn't snap in half from waves. And one we're exploring is if we're exploring the failure probability of autonomous control over a different set of test characteristics, what is that probability of failure and how can we get to that more quickly? So these are some applications in our domain, but I'd be really interested to hear from any of you in the audience that have ideas of where it might apply to your domain. So, opportunities and challenges. What are some of the things this gives us, and what are some of the areas that we foresee there's further work required? Measuring uncertainty gives us a way to navigate some of the challenges we face in this physical world where we have a really high cost for making mistakes. And we think it's likely to be a big part of being able to scale AI into an industrial safety critical context. One of the advantages is often once we know our uncertainty, we can live alongside it. We can either come up with different methods or approaches that help us navigate it, or fail over systems that can take control when we're too uncertain. In addition, in the physical world, often we can collect more information or more data. We can run more experiments. And so having a measure of uncertainty and how that affects what we're doing allows us to more efficiently allocate resources to doing that. Some of the challenges is that if we're relying on our uncertainty estimates to make critical decisions, we then need them to be accurate. So it introduces a new area where we have to take a bit of care. Additionally, there's a technical overhead to employing these uncertainty-aware approaches. We now have to propagate distributions through our system rather than point estimates, and we've seen that this has been particularly challenging, for example, for our engineers who aren't experts in this field. So we need to make this more accessible if we want it to find more widespread adaptation. And this is something that we've tried to do with that software package, Xtrain. Finally, it takes computational effort to come up with these uncertainty estimates. So if you're operating in a compute-constrained environment, you have to make a trade-off between how much compute am I going to spend on my uncertainty and how much compute am I just going to spend trying to get the best possible average estimate. And that's a decision you have to make based on the situation you're in. So that's all I have for you. Thank you very much for your attention. I hope you enjoyed it.
Thank you, Sebastian. Questions? So I'll start, and if there's any questions online, please post them. I was going to ask the same question I asked the first speaker about, we know models often aren't perfect representations of reality. Is that something you worry about when you think about uncertainty in decisions?
Not particularly, and that's not because our models are perfect, but the degree to which they're right, the uncertainty introduced by that is far smaller than the uncertainty that comes from other areas of the calculations, right? So in terms of like our priorities, of course, it has an influence, but there's other areas that are much more likely to have a big impact that probably aren't completely solved yet and are more worth spending our time and attention. So it's a really good question because, of course, the engineering or finite element models are not perfect, but their error in comparative to the other factors that are involved here is relatively small.
Right. Okay. And along those lines, one of the things you can do is to grade your simulator with multimodality approaches. Are they kind of the methods you're looking at as well, or?
Yeah, that's a possible future direction. So we've started off kind of simple because we want to get this into the hands of our engineers to start getting some feedback and understanding, well, like what are their critical issues, and then we can do further research into those and prioritize that way. But it's definitely something we're considering.
Great. Please.
Thank you. Very interesting. You talked about extending methodology from 1 hour to 2 hours out to 20 years. Could you talk about some of the assumptions that you make in that extension? Because, for example, the likelihood of getting extreme weather for 1 hour versus extreme weather continuously for hour after hour after hour for 20 years, there's a sort of the independence. It looked like you were assuming independence there, and it wasn't clear if that was the right assumption, but I might have missed it.
No, that's a really good question. So I guess there's probably two parts to it. One of it is that commonly in the engineering field, when they do this, they assume independence because we're operating over such a long time scale. Right? So yes, clearly 1 hour weather periods are not independent because a storm is not going to last for 1 hour and then you're going to get calm seas. But when we do this for 20 years worth of time, we can roughly take that on average. And so one of the parts I didn't talk about in that extension is when we get this CDF, first we marginalize out the impact of weather. So what we do, and that was part of that equation, is we use importance sampling to cover a wide region of possible weather conditions and then come up with an average CDF, which represents what is the average response in 1 hour.
So the way I understand, you want to replace the simulation with surrogate simulation based on data, right? Have you looked into, there is an area called physics-informed neural network modeling of physical system. So you can, instead of simulate, you can mimic the simulator using the PIN, which is physics-informed neural network, to model your wind turbine system or any physical system. So that could also replace your surrogate model, and there is no simulation involved. And also about your Gaussian, non-Gaussian, are you using some Kalman filtering? What kind of, like, how you're making non-Gaussian noise go away, like, because you are ultimately having Gaussian in the before the output.
So what we do there, I'll answer your second question first. What we do, we run the simulator many times at a given X input point, and that gives us then you have like a data that you can fit a distribution to, right? And if you use MLE to fit that distribution and estimate the parameters, then you get for example, the location and scale of a Gumbel distribution, right? And if you use maximum likelihood, then your uncertainty in those distributions is also normal, I think in the limit. And so what we do is we use a Gaussian process to predict those parameters, location and scale, and then we get our distribution that we work with for downstream tasks. And I've forgotten your first question.
Well, first question was that there is a physics-informed neural network modeling area where you can model any physical system based on physics domain plus neural network, some data you also need to train it. So that can also replace your surrogate simulators.
Yeah, it's an area I haven't looked into too deeply. One of my One of my concerns, I guess, there might be how much data is required to train a pin, right? Because we're trying to use as few simulation runs as possible. So if that works with a low number of data points, then that's something I'd really like to discuss.
Okay, great. Let's thank Sebastian again.